Good morning, good afternoon, good evening. So thank you all to join us again for this CASS talk that is organized by the IEEE Circuits and Systems Society Rio Grande do Sul chapter in cooperation with the graduate program Microelectronics of the Federal University of Rio Grande do Sul, also in cooperation with the Brazilian Computer Society, Brazilian Microelectronics Society. So today we have the pleasure to have a talk by Professor Claudio Diniz from Federal University of Rio Grande do Sul in Brazil. But before giving the floor to Professor Matheus Glerert from the Federal University of Santa Catarina, that will be the chair of the session today, just some brief announcements. So next week is a special week because we are starting the Industrial Talks 2021 with a very special talk by Alan Wang from Insilica, UK. And it's really special because also it will be included in the session the announcement of the establishment of Insilica Brazil at Porto Alegre. So this will be done by Dr. Júlio Leão. And the talk by Alan Wang will be about enabling the next generation of always connected cars. So a hot topic nowadays. So now also the chapter of Solid State Circuit Society and the Electron Device Society South Brazil are also joined as a co-sponsor of this series. No, it's not included in this flyer yet, but it will be done soon. And the week after, the day after, we have the next CASS talk next week on Friday by Dr. Vladimir Alves, CTO at NGD System in USA, talk about computational storage and its applications for machine learning. So Professor Dr. Vladimir Alves was a former professor of Federal University of Rio de Janeiro, but he's living in USA. He's working in industry since more than 15 years now. Then the week after, we have a Professor Hao Kai from Southeast University of Nanjing in China, talking about energy efficient in MRAN computing. So another very interesting talk. Then August 6, I don't have the flyer here, but it's a professor from Spain. This will be announced next week. And August 13, we have Professor Luciano Agostini from Federal University of Pelotas, Brazil, talking about video coding, state of the art and trends. Then August 20 is Professor Malgorzata Jeski from Portland State University. And she's going to talk about heterogeneous integration, 3D systems and emerging devices. Then if you lost the special event that was organized about the assessment in higher education and research, the recorded version is available in this YouTube channel. So both the talk of Professor Michel Robert and the panel, including Professor Raimundo Macedo, Professor Marcelo Lubaszewski, Professor Thiago Bari, and Professor Avelino Zorzo. And if you lost also the talks in 2020 and also some talks in 2021, so the recorded sessions are available at this YouTube channel and much more, also as some invited talks of the Microelectronics School, the invited talks of the DPV SCA. And so going there, you can, if you want to see the full playlist, because there is a limit of the number of talks in each row of YouTube. But if you want to see the full playlist, you have to scroll, and then you can ask for the full playlist. You are going to see all talks and in each category, and we have more than 90 talks available there. Also, reminded that it's becoming close now. You have about 1.5 months to prepare a nice paper to be published, submitted to LASCAS 2022 in Chile. I hope that we'll be able to be face-to-face conference or hybrid one. And as you know, a set of extended versions of best papers are published in TCAS 1 and TCAS 2. And the one selected for TCAS 2, this is done before the conference. And then you have the papers published in addition of TCAS 2 in the moment of the conference. And then in the proceedings of the conference, you should have only the abstract because the full paper is in the journal. And considering also the presentations, there is a selection of papers to be submitted to TCAS 1, and then it's a really extended version of the paper that will be published later. So it's scheduled to December this year, the selected papers from LASCAS 2021. And then LASCA 2023 will be in Ecuador and 2024 in Punta del Este, Uruguay. Also, it's open the selection for the master program of the graduate program on microelectronics at the Federal University of Rio Grande do Sul. So anybody from any country is welcome. And the submission of the proposals are open till the 23 July, so next week. And the submissions for the PhD program is always open. So there is no specific limit. So each month you can do your application. So also just a reminder that if you are not yet a member, or if you have not yet renewed your membership for 2021, there is still available 50% discount for student and graduate student membership. And as you know, the student and graduate student membership, the amount is the same. So if you are in a graduate program, and if you have not yet done your upgrade to graduate student membership, please do it, because then you have rights to vote and other benefits. And then you just have to use the code Future50. But today we are here to attend the talk by Professor Claudio Diniz. And so thank you very much, Claudio Diniz, to accept our invitation. And thank also very much to Professor Matheus Grelert to accept to be the session chair today. So I give the floor now to Professor Matheus Grelert to start the introduction of Professor Claudio Diniz. Thank you very much.
Thank you, Professor Ricardo. Thank you, everyone, for being here. I'd just like to say that it's an honor to present my friend and someone that I admire so much, such as Claudio. For those of you who don't know me, I am Matheus. I work at the Federal University of Santa Catarina, and work with embedded systems, video coding, and machine learning. Many of these researchers are actually with the cooperation of Claudio, so it's very easy to introduce him to you guys. I'm not even going to read his CV. I know Claudio since forever. We met when I was still an undergraduate at ISCAS, and he graduated in computer engineering back in, I don't remember when, 2007? Is that it, Claudio?
Yes, 2007.
And he did his master's and his PhD at the Federal University of Rio Grande do Sul. During this period, he spent some time at the KIT in sandwich doctorate, during which we also had a few experiences together, because I was also in Germany at that time. I received him and welcomed him to Germany. And we've been working in research together since a long time ago. I don't even remember when. We also were colleagues when Claudio started his professor career, his academic career as a professor. We were colleagues at the Catholic University of Pelotas back in 2017 when you entered, right? And then I was in 2018 or something like that. And his research is basically surrounding hardware aspects of video coding solutions, using techniques like approximate computing, efficient hardware techniques for low power video coding applications. And without further ado, I'm gonna leave you to Claudio. And thank you very much once again, Claudio, for being here with us.
Okay, thank you very much. First of all, Professor Reis, to making the invitation, and also it's a pleasure that Mateus is chairing this session, because we are, as he said, we are colleagues for a long time.
Colleagues and friends.
Yeah, and friends. First in the PhD, masters, and then as a professor at the Catholic University of Pelotas. So I don't know if you have the administrator have to change the slides for me, because I don't have this permission. Okay.
Yeah, there you go.
Okay, thank you. So thanks, Mateus, for the introduction. Now I'm going to talk today about approximate hardware accelerators for video coding. So thank you also for people. I see many friends here and colleagues watching today live in YouTube. So thank you very much for attending this session. So now I'm the Federal University of Rio Grande do Sul. I'm a professor at the Informatics Institute at the Microelectronics Group. So let's start. So, well, as you know, the internet video is here. We have a huge demand today for video over the internet. We are doing it now, by the way. And here are popular video on demand and video sharing devices like YouTube that we are using now. It has more than 2 billion users and 1 billion hours of video is watched daily. So it's an impressive number. And we have also other prominent video on demand service like Netflix, Instagram. Also, the CTO of Instagram said that it's not anymore a photo sharing app. Is like they are investing now more in video, and they have also more than 1 billion users. So it's also an impressive number. And we have also another service like Amazon Prime Video, the Disney Plus, that is a very new service that it has only 2 years, I think, and it has more than 100 million subscribers. So it's also impressive that in 2 years they have this number of subscribers. And we also have the Chinese TikTok app that is also very popular in the world. Also, we have a huge demand for video conferencing, which is primarily driven by the COVID-19 pandemic, right? The company CASS estimates this number of increase, like 285% increase in voice over IP and video conference usage due to the COVID-19 pandemic. So we have today popular service with more than 100 million active users per day. So you have this service like Google Meet, Microsoft Teams, Zoom, and WebEx by Cisco. And we also have a huge demand of live streaming that we are doing now through YouTube, and we are using this new service called StreamYard, for example. But we have also the Facebook Live service, this Facebook Watch. We have also Instagram Live Stories. We have also Periscope, that is the oldest one. And people that like gaming, they normally use Twitch, which is also a very popular live streaming app. So there's a huge demand for video today over the internet, and all the services are over the internet. Actually, Cisco, since some years ago, they published a document called Visual Networking Index for forecast and trends. So they try to estimate for some years in the future the size of internet traffic, right? So they estimated in 2017 that the traffic over the internet is going to increase about 26% per year. And this was the last visual networking index forecast document. And an interesting thing to note here is that the traffic over smartphones is increasing dramatically, and the traffic over PCs is decreasing. So the number of the traffic the traffic is over PCs remains the same almost, but the percentage of the traffic over PCs is decreasing, right? And the percentage over mobile device like smartphones and tablets, mostly smartphones, are increasing dramatically. You can see in the graph here. And also it's interesting for us that work with video that they try to estimate the video traffic. So they estimated that the video traffic by 2022, so next year, will be 82% of all IP traffic. So all the data that is transmitted over the internet, 80% is video data, okay? And this was increasing from 2017 up to 2022. And it increased, it will increase fourfold in this period, okay, 4 times. So it's a huge increase in the traffic. We can see here in this slide the reason for the increase. The reason is that people are using more high resolution and ultra high resolution videos. Okay, so the standard definition videos remains almost the same. It has a very small increase, but the sorry, okay. But the number of exabytes per month related to high resolution videos is increasing dramatically, okay? And the percentage is also increasing. And we see here in mostly in by 2018 an increase use of ultra high resolution videos, that is the 4K and 8K videos, especially the 4K videos, okay? Also, we are seeing an increase in the video resolution of flat panel TVs. So the number of the connected 4K TV sets, that TVs that support this resolution, is increasing every year with a rate of 38% per year. So it's a dramatic increase. So it's also very impressive. And the most service that we see that I mentioned before, for video over the internet, we can see in these TV sets, okay? Because they have apps in the TVs to we call the smart TVs to see these videos. And we have also another new thing that is coming now, that is virtual and augmented reality traffic. So virtual and augmented reality is being used more and more. So we have here a 12-fold increase from 2007 to 2022. So it's very impressive. Also that this kind of device is being more used nowadays. Okay, so this is the motivation for video usage, and we have to see now how we represent this video. So in a raw video representation, we can see that this is not a possible video representation for video over the internet because it consumes a lot of data. So imagine that we have a video that we represent each pixel, the picture element, in 24 bits, so 8 bit per color channel. Normally we have 3 color channels. And transmit it with 30 frames per second. This is the bit rate that we have for different video resolutions. So for the standard definition, that is this resolution in pixels, we have about 200 megabits per second. If you use now the full HD, the 190/20 by 1920 and the 1080 pixels, we have the bitrate of 1.49 gigabits per second. And if you use the 4K, the ultra high definition 4K, we have 5 gigabits per second. So this compared with the network speed that we have in our device, it's not possible to handle this video representation, because this is the another prediction by Cisco of the network speed by 2023. So the average fixed speed in the world is 110 megabits per second, the fixed connection, like Ethernet. If you go to Wi-Fi or mobile, we have like 90 megabits per second, 44 megabits per second in mobile. So it's not possible to handle this kind of video representation, okay? So we have to compress video. So by the way, all these services that I mentioned before were possible because of video compression. We actually use, we are using now video compression. So my video is transmitting to you in a compressed form. And so I have here a video source. My camera of my computer is taking the video of me, and I have a video encoder somewhere that is compressing this raw video representation into a compressed form that is consumes a lot of there's a lot of reduction in the number of bits in this bit stream in the video in compressed form. And so the video in compressed form goes to the network, goes to the internet, or goes to a storage device. And then when people want to see the video, then they need a video decoder to decompress the video to display it in a display. Okay, so this is the flow that most we use nowadays to handle video transmission or storage. Okay, we actually have video coding standards to compress a video signal, because we have to guarantee that this video decoder is compatible with these video encoders in order that this video is being reconstructed in the device that is receiving. Okay, and so we have standards. Okay, and mostly the video coding standards define the video decoder. So they define the video decoder and also this input bit string syntax. That so there's a rule to build this bit string syntax and the video decoder in order that the decoding, the device that is receiving the video, is displaying the video, is going to display the video that's generated by video encoder. So the video encoder only needs to generate a compatible bit string syntax. So they don't need to implement all the features that is defined in the standard and the video decoder. So it's very good because the video encoder is open for optimizations, because they only must generate a complete bit stream. And mostly in this consumer electronic video, we have video encoders that introduce losses in the process. So there is a lossy compression, and the goal is to maximize video quality of the decoded video and to minimize the bit rate of the bit stream. So it's sometimes a challenge, because we want to maximize quality, but we also want to have the minimum number of bits here in this encoded video representation, the compressed video representation. Okay, so it's most of the times a challenge. So in this talk, we will focus on the latest standards that are developed by ITU, that's the International Telecommunication Union, and the ISO, that is the International Standardization Organization. That they have groups like MPEG and VSEG, that they join a group of experts in video, and they developed in the past last years the high efficient video coding, the HEVC, which has this numbers of this is the number of documents that became famous, like H265 and the ISO 2300882. So the HEVC is published in April 2013, and it has already a 50% bitrate reduction compared with the very well-known H264 MPEG-4 AVC standard, the Advanced Video Coding Standard, that has is mostly supported in the market now by most of devices support this standard. So HEVC has already a 50% bitrate reduction for the same quality, right? And now, very recently, we have the versatile video coding, the VVC. It's called the H266 by ITU, and this number in ISO. And it was published in last year in July. And it has also a 50% bitrate reduction compared with HEVC. So it's also an impressive number, because in each generation of video coding standard, they try to reduce bitrate by 50%. This is for the equal subjective quality. We are going to see that objective quality, it does not achieve this number of 50%. So the new advanced video coding standards they follow since AVC mostly. They follow this diagram here. This is a video encoder. So it's a block-based hybrid coding, since they try to so they split the video into blocks. The video frames are split into blocks, and each block of the video frame is passes through all these blocks. I'm not going to explain all the flow, but I want to highlight here the prediction phase. So based on the raw original input video, they try to derive a prediction, and the prediction is subtracted by the original, and which generate a residue. So residual blocks are sent to transforms and quantization steps, and further to the entropy coding. And then we generate the output bit stream. So this is normally the flow of encoding. Transforms, we use mostly integer approximations of the discrete cosine transform, the DCT transform. And the quantization is the main phase that introduces losses in the video compression. So we have also a parameter that controls these losses, that is called the quantization parameter. Then we have entropy coding, that is a lossless process that further compress this quantized coefficient, and now this information that is called we see here, that we are going to detail in the next slides. We have also this decoding inside encoder that is necessary to generate reconstructed video. So we have here inverse transforms and rescaling to, and then we sum to the predicted samples to reconstruct. And we have also filters here to generate this decoded picture buffer that is used to generate reference frames that are used in this size of this kind of prediction, the inter-frame prediction that we are going to detail in the next slides. So the video decoder is more simple. We have entropy decoding. We have here the input bit stream that is generated in the encoder. And you have entropy decoder, inverse transforms and rescaling, and also the intra-frame prediction, the prediction phase. So note that we are also doing prediction here in the decoder to sum to the residual samples to generate the reconstruction samples. But note that this decoded video is not the same from the original video, because you have losses mainly here in the quantization, but also in the prediction, but mainly in the quantization step. So the decoded video is not anymore the same original video. So the goal is that this video is most similar to the original one, okay? And we can also measure this quality. So this flow is the same for HEVC and VVC, and also for AVC, but there are many new features in the HEVC and VVC standards. In the HEVC, mainly the block partitioning is more flexible. So we can partition blocks first in coding 3 units. So we first split the video into coding 3 units. We have this maximum size of a luminance coding 3 block that is 64 by 64 samples. It's larger than AVC, because AVC used a macro block that is 16 by 16 samples in luminance channel. But in the HEVC, we can recursively partition the CTU into coding blocks using quad tree partitioning. So we can build this quad tree, and we can do a partition like this in a square. We are recursively partitioning coding 3 units in a quad tree manner. So we have always squared blocks here with different size. This partition can adapt to video content. So if you have homogeneous regions, you can use larger blocks, and if you have more texture and more heterogeneous regions, we have to use smaller blocks. In the VVC standard, we have a more flexible partitioning. So you can recursively partition now with a quad tree, but also with a multi-type tree partitioning scheme that allows also binary and ternary split. That is not allowed in HEVC. It's allowed in some cases, but not for all the block types. Okay, that I will explain the next slide. So VVC tries to make it more flexible, and they also in the standard they also increased the maximum size of the block for 128 by 128 samples to adapt to ultra high resolution video content. Okay, so this is the comparison between HEVC block partitioning and VVC block partitioning. And so in the HEVC we have the quad tree partitioning that is allowed for all the in the HEVC we have one concept like the block types, like we have coding units, we have prediction units and transform units. So we can partition in quadratary way for all these blocks, but especially for intra-prediction units, we can also have some kind of binary splits, but not ternary, right? And the VVC, they removed this concept of prediction units and transform units, and they allow all this kind of block splits, block partitioning, but we have also some restrictions in the recursive partitioning using these modes, but we have a more flexible partitioning at the end. So and then what we do with these blocks, we do prediction. So we have intra-frame prediction. So we take one of these blocks that are already partitioned in the first phase, and we do a prediction based here in the inter-frame prediction. The predicted block is calculated from samples of the neighbor and previously encoded blocks that are already reconstructed with losses at the encoder. And these neighbor blocks are from the same picture. So it's actually a image compression scheme, okay? So inter-frame prediction is actually an image compressor. Here are some examples. This is an example of angular intermode in HEVC. So that is it tries to emulate some textures, and we have a set of angles that we can predict the blocks, and the samples are generated actually by filters that for each of these angles. These are the intermodes, the angular intermodes, the angles that you can predict. We have 35 intermodes in HEVC. 33 are angular intermodes, and we have also planar and DC that are another. I'm not going to detail this. The message here is that VVC increased the number of intermodes to something like 80 while HEVC will have 35 here. So we have now more angles, and also we have wide angular interprediction modes to generate these ones that are in dark gray here, light gray, sorry. So there's more modes to exercise. We have also this tool that's a very important tool that is called intra-frame prediction. It is separated in two steps. The motion estimation is only present at the encoder. It finds a motion vector for each block to be encoded based on reference frames uses block matching algorithms. So the process here is for each block to be encoded, the current block in the current frame, we have to search for the most similar block in reference frames. And these standards support several reference frames. When we find the most similar block that is in red here, we derive a motion vector, and we encode only this motion vector and also the difference between the current block and the most similar that is not equal block. And we encode only the residual block and the motion vector in the next steps, like transforms, quantization, and entropy encoding. So the motion vector is actually a vector that points from the position of the current block in the reference frame to the position of the most similar block. Here we see here in the at the left of the slide. And motion compensation does the opposite. It receives at the decoder the motion vector and derives a predicted block based on this motion vector received in bit stream. So they fetch motion compensation fetches in the reference frame this most similar block. This is the prediction. They have also to sum this prediction with residual block to reconstruct the block, as we said before. So all these steps, you can see that both in intra-prediction and inter-prediction, we have, at the encoder side, we have a lot of coding modes and possibilities to encode. In the intra-prediction, we have a lot of intra-modes that we call for encoding each block. And also we have all the partitioning possibilities. And also in motion estimation, we have all these partitional possibilities to do the motion estimation. So you have to decide which coding mode and which partitioning option we are going to use to encode a particular video. And this process uses rate distortion optimization that we called in the community RDO. The goal of RDO is to minimize minimize the bit rate, and minimize the distortion of the coding mode and partitioning option for each coding unit, for each block that we're going to encode. And it's formulated with this optimization problem. This is not normatized, so we can use any method, but most video encoders use this kind of this method that's very famous for a couple of years. It is very used. It's very efficient also. And that's the J equal to D plus lambda multiplied by R. So D is the distortion introduced by the prediction. R is the bit rate of the coded block using this prediction, and the lambda is a Lagrangian multiplier. That is a constant, but it's based on the quantization parameter, that this parameter that controls the losses of quantization. Okay. So the goal here is to find the mode, the coding mode, and the partitioning option that minimizes J, the parameter J. That is the cost. And we have here the, it's not exhaustive because it is not possible to do an exhaustive because you have many, but it's the most custom, the most efficient process. That is the full RDO that is explained in this figure. You do the prediction, you do the residual generation, the prediction for each block, for each partitioning option, and we do transforms and quantization and entropy coding. Then we take the bit rate of this coding mode, and also we have to apply inverse transforms and inverse quantization, add to the prediction, calculate the distortion, that we are going to see how to do this. So after calculating the distortion, we have a loop here because other prediction use this, actually these predictions for other predictions, but in the distortion calculation, we calculate the distortion, and we have a block called the mode decision that decides which mode is going to be used to encode that particular block partition that based on the bit rate and the distortion that is calculated. And here we have the best mode. Okay, this is done only at the encoder side. The decoder only applies, only do the prediction of the best mode and do the inverse transforms and quantization and reconstruct that particular block. The encoder is much more complex compared to the decoder because of this process here. That you have to decide. It's an optimization problem. And how we calculate the distortion using mostly these metrics. We have here the sum of absolute difference, the SAD. that calculates the distortion of a predicted block used as reference compared with the original block. Okay, so we subtract pixels here from the block, and the block size is n by n, the block size in samples, and we take the absolute, the module, and sum all this difference, the absolute difference. So the name is very says what it is, sum of absolute difference of the samples from the predicted block to the original block. But we have only one original block, but we have a lot of predicted blocks for different coding modes and different partitioning options. So this is often used in integer motion estimation. Why I mention integer, I forgot to mention that the motion estimation we can also do in the HEVC and VVC standard using fractional pixels. So the motion vector has a precision, a fractional precision, like a half sample, quarter sample, and we do interpolation to generate these fractional pixels. So this increases the performance of motion estimation, and it does a better prediction. And we also have a more efficient distortion metric. It approximates more to the full RDO. That is called SATD, the sum of absolute transformed difference. They calculate a distortion introduced. It does the same thing compared with SAD, but using a Hadamard transform. That is a simple transform. This is this. We can use a lot of different sizes, and we have here the residual block, the difference between the original block and the predicted block. But the difference is now transformed before taking the absolute and adding the absolute difference. So this is the transform matrix that you can use. They are Hadamard matrix. It's a very simple transform because it has only 1 and -1 coefficients. So we don't have to use multipliers here. We only have to use adders and subtractors. And we use different sizes because most because of the size of the blocks. For larger blocks, this one is more efficient. So because of the introduction of losses, we have to measure video quality. So the losses, the quality, the losses in quality that we have when we compress a video. There are two classes of techniques. The subjective techniques. They are based on mean opinion score. So it's people watching videos and giving grades to the video quality. It's a very complex process, and also it is also normatized. There are also some standards to do subjective quality, and we need people to do this. And we have also objective metrics that you can calculate. There are mathematical formulas. The PSNR, the peak signal to noise ratio, is a very famous metric that is used in this scenario here, and is still the most used metric. It has some problems because of it is based on mean squared error, so it loses the structure of the image, but it can measure quality, and it's a logarithmic scale objective metric. So this is done by MSE. So we calculate with MSE the between pixels from an input image and an image after compression, that is K. So we take the subtraction. We have to square this difference, and we sum and then divide by the size of the picture. We have MSE. Then you put in this formula and you have PSNR here. So a larger PSNR is a good image. It has a few losses compared with the original raw picture. And we can, so measuring the video quality, we can put having also the bitrate of the coded video. We can generate these curves that's called Rate-distortion curve. These curves are used to compare the compression quality of different encoders or encoder configurations from the same encoder. So each curve is a result of one video encoder configuration, one run of one video encoding a complete video. So we can plot here these curves, and the curve that is above the others is the better performance because it has also a better quality for the same bit rate, and also a lower bit rate for the same quality. It works for the two things that we can compare in the quality perspective and also in the bitrate perspective. This is an example from this very new paper that is comparing the encoding of the cat robot one video sequence. That's a ultra high definition video sequence we using VVC. That's the newest standard, the HEVC and the EVC. So you can see here that VVC has the best performance. The HEVC is in the middle and the EVC is in the bottom, the lowest performance. So we can see here the for each bit rate the quality in PSNR for each different video coding standard. For example, in this bitrate 15, we have 39 dB of PSNR in AVC and increased to 40 for HVC and about 40.5 in the VVC. This is in the logarithm scale, so small gains here means a lot. Okay, small gains in PSNR means a lot. And we also can compare in the for the same quality the bit rates. Okay, and also to synthesize these curves, we can use this metric that is the Biontega delta metric that compares two Rate-distortion curves using curve fitting with 4 quantization parameter points. So we take, as we see here, we have 4 points for each curve because they did not run for all these bit rates. They run it only for these 4 points, and this is a curve fitting. Okay, there's another point. There's other points here that are not shown is curve fitting method. So they run 4 times for each encoder, and we can compare 2 curves and synthesize into a number. So we can use a BD rate, that is Biontega delta rate. There is a bit rate increase in % for equivalent video quality. Consider these 4 quantization parameter points that define 4 different video qualities. And also you can calculate the Biontega delta PSNR. That's the PSNR difference in dB for equivalent bit rate. Okay, it's a very old method, but it is most used for HEVC now and VVC. Okay, so we can see here the rate distortion comparison. So actually VVC is superior with HEVC. Okay, we have this paper has a lot of results actually this paper don't have results, but we have a lot of papers comparing the distortion curves of the encoders, and it is also done in the encoder standardization process. But what is the complexity of this increase? So some papers analyzed the complexity of one video encoder compared to a previous one, based on encoding time or cycles in the processor, this kind of things. So this analysis was done with software profiling used Intel V10. It is a comparison between the HEVC and VVC. So we see here that they ran a lot of videos, and they summarized the results in this table. So we have here the encoding complexity. It increased up to 3 times for this configuration. These are some encoding configurations. This is all intra, codes only intra prediction frames. This is random access that uses interframe prediction. These are other encoding configurations that are also using interframe prediction that's more complex. And the encoding complexity is increased a lot, like 1.2 times, 1.5 times for this video sequence. And we have also the decoding complexities increased from HEVC to AVC. Okay, they have done this with the reference softwares. They are open, available in these websites here that are maintained by the Heinrich Institute in Fraunhofer Institute in Germany. And we also have here the bit rate increase from comparing HEVC to AVC. So we have here not a 50% because it's subjective quality, but in the objective quality we have something like 35% or 40% of bitrate reduction for the same quality when we compared HEVC with AVC. And we also have here papers comparing the VVC, that is from the last year, and HEVC, that's from 2013. This analysis was done also with software profiling by the same group. And we can see here another increase in compared with AVC, that VVC is producing. So we can decrease up to 33% the bit rate for the same quality of a video if you use VVC instead of using HEVC. Okay, but the encoder complexity is increasing more complex in the encoder, in this random access encoding configuration, and we have in our inter 34 times more complex. But the decoding complexity it not increased a lot, but increased almost 2 times. And this complexity increases are very challenged to do what we are doing now, that's live streaming. We have to encode now the video and transmit, and then the people that watching are going to decode. So keeping the live streaming that we call the real-time encoding. We have to do real-time encoding to enable live streaming. It's very complex to do this if we have a complexity increase like this, because HEVC is already a very complex standard for real-time encoding. Okay, and we have also the VVC reference software now. It's already available since last year. Sorry. So we can do this analysis by ourselves also. So this is the motivation of the video coding. I want to discuss now with you the current challenges for process architecture and integrated circuit designs. Integrated circuit designs, as we are seeing this huge complexity increase of video encoders of these new standards, and it is going to maybe keep for the next standards. We have to see what we have in hand now for enabling real-time video encoder, right? So is that possible? So we know we are like in circuits and systems community. We know Moore's law and Dennard scaling. That has driven the evolution of the computer devices since the last 50 years. So Gordon Moore said in the 70s, actually in the 60s, but he have done a different prediction in 75 that the number of transistors in a dense integrated circuits doubles about every 2 years. So every 2 years, the number of transistors was doubling in that time, and it is already keeping. It's already a reality now, and this phrase was called Moore's law for in that time because this law, this prediction, remained true for the couple 50 years. And also you have the Dennard scaling that is not as famous at Moore's law, but it has the same importance that Robert Dennard did in 1974, that the transistor density increase. As the transistor density increased, the power consumption per transistor would drop. So the power per millimeter square of silicon would be near constant. So in each integrated circuit technology node, the power per millimeter is constant. So we can fabricate, we were able to fabricate a new technology node not consuming more per millimeter. So the power density was remaining constant. Okay, and this was also true for a couple of years ago, but we are seeing a drop of both Moore's law and Dennard scaling. Actually, this is a graph from Hennessy and Patterson paper from 2019 that compares the Moore's law version and the density. This is the Intel microprocessor density that we have since the 70s until now. So we can do this time series. And then Hennessy and Patterson did this time series and observed that the Moore's law began to slow here around year 2000. And actually in 2018, we have a 15-fold gap. So the density actually 15 times less than the predicted by the Moore's law in 75. Okay, so we are not seeing the same integration increase, the exponential integration increase of transistors as Moore's law predicted in the 70s. Actually, Gordon Moore itself said in 2003 that no exponential change of a physical quantity can continue forever. He did this talk in ISSCC in 2003. This is being delayed with the new technologies like 7 nanometer technologies. New devices are trying to integrate more and more transistors, but it's going to fail sometime because of physical limits. And also the Bernard scaling is not, the power density is actually increasing, is not remaining constant, and also from 2007 mostly, when technology nodes became a nanometer, like a decade, in these new technology nodes from 2007 and on, the power density is increasing a lot. So in order to remain the power in a controlled point, we are seeing this phenomenon of that the CTO of ARM in 2009 called dark silicon. Dark silicon is an area, is a phenomenon that in the new integrated circuits, we are able to build dense devices. We are able to, because it follows the Moore's law. It still follows the Moore's law, but the Bernard scaling has failed. So we can build dense devices that they cannot afford to power, said Mike Miller in 2009. So the message is that we cannot turn on and switch all the transistors all the time. We have to turn off some transistors or operate a large portion of transistors with lower frequency, operating frequency. Okay, so the first estimations in 2010, this phenomenon was studied a lot from 2010. They predicted around 8 to 9% of dark silicon chips, but actually we have 30% in low power modes to 50% in high performance modes. So 50% is actually a lot, and we have to handle this. So most people are handling this with turning off cores of the multi-core system. So multi-core was actually a response for this scenario here, and this and also for this Bernard scaling failing scenario. But we are seeing now a trend of using a more efficient computing of complex tasks using hardware accelerators, because a multi-core is not addressing this hard task that is due to these things that I mentioned before. So actually, Hennessy and Patterson included in their book a whole chapter of domain-specific architectures, and also people are calling this hardware accelerators with different names. We have accelerator-rich architectures from Jason Kong in 2014, and so on. So in a recent paper, Hennessy and Patterson also state the benefits of hardware accelerators. There are more efficient form of parallelism for a specific domain. So the message here that they are specific for a domain, like video coding, for example, like neural network processing, for example, neural networks. They are more effective in the use of memory hierarchy. They are more effective than general purpose caches, for example. We can use less precision when adequate. So we can use, for example, in the video encoders, we have some videos with 8-bit per sample. Other videos are 10-bit per sample. So in the 10-bit per sample video, you don't have to use 16-bit register. We can use a 10-bit register. So you can target this precision very efficiently when you build a hardware. And we have also the benefit from programs written in domain-specific language that are also being mostly used now, like the neural networks. We have TensorFlow, for example. These frameworks, and we are we are looking for the emergence of more domain-specific languages for domain-specific applications. And we also can combine here the approximate computing concept, because the approximate computer is the ability of many systems and applications to tolerate some loss of quality or optimality in the computer result. And also we can relax the numerical equivalence between specification and implementation of error-tolerant applications. Okay, so the message here in the approximate computing is that we in traditional computer world, we are also we are already approximating the application with approximate and probabilistic algorithms, and we have also an approximate behavior in the devices because of software errors and timing errors. But we are keeping the numerical and Boolean equivalence in the language, compiler, system software, architecture, logic blocks, and secrets. So the message here is to apply approximate computing in all the computing stack. So we can approximate all these levels, like the secrets, logic blocks, architecture, the language, the compiler, the system software. So the talk here, it's a very big introduction, but I want to talk about some of the works that we are doing in this field of hardware accelerators for video coding. We mostly used SATD, like distortion metrics as case study, so SAD and SATD. And why we are doing that? This is because they have average shares of the execution time in modern encoders. You can see here in HEVC, in this paper, the profiling results show that the SATD and SCD combined have 36% or more than 40% of execution time share in the whole video encoder. And it also remains true for VVC. The Mateus is going to recognize this picture because it's a paper from his group. Here we can see the percentage, the average time is spent in motion estimation, motion compensation steps that are using these distortion metrics. Mostly this affine mode, that's a new mode that is I did not mention here because of time. That do motion estimation. It does motion estimation with non-translational motion. And the EME, the integer motion estimation, does only with translational motion that I mentioned here. And we have also fractional motion estimation here. So a lot of this is a contribution of the tools of motion estimation, but the message here is that motion estimation consumes the largest part of encoding time. Okay. Because of the distortion matrix calculation. So this is the first case study, the SATD. This is a work that we did in published 2016. So we take a precise SATD hardware accelerator for using 4x4 Hadamard matrix, and this is the internal organization of the vertical and horizontal transforms, because we can split the matrix multiplication, this transformation in a 1D two 1D transforms, the horizontal and vertical. And we applied approximation using a technique that we call it coefficient pruning. So we prune some coefficients, we exclude some coefficients from actually the vertical transform. So we apply the horizontal transform, but the vertical is pruned. So we have here a reduction of the number of adders and subtractors compared with the original one. You can see here. In this, we are approximating the SATD calculation in the architecture. So this is an approximate hardware accelerator. Okay, and we have to analyze the quality of doing this. So we did in that time some evaluations in HEVC because VVC is not available yet, and we see here a small drop in BD Beyond Delta bit rate metric. It's a small drop, like less than 1% bit rate increase when we approximate compared with SATD in a precise form. And we also compared with SAD because this is the simple metric that is can use it instead of SAD that they did not have. This metric doesn't have a transform. So we can use also SAD as an approximation of SATD. So as we are approximating SATD, we don't have to have a worst BD rate result compared to the SAD. So this has driven the number of discarded coefficients that we can have. As we have a 4x4 matrix, we have in total 16 coefficients, and we saw that we can most of the times discard 10 coefficients, and we are above the SAD values. And then we derive some hardware accelerators, approximate hardware accelerators for SATD. And then we compared with precise SATD and also SAD. We can see the power, the dynamic power, and also leakage power reduction here. That is very interesting. It actually has more power than SAT, but SAD has a more as a less efficient distortion metric than compared to SATD. Okay. Then we did another study. Okay, let's look more in the architecture way, and let's remove the vertical transform. Let's do SATD only with horizontal transforms. So that's what we did in this work. We did some new architecture with only 1D transform, the horizontal transform. Then here we have the sum absolute values that we have also here in this slide here. And then we saw also a small compression increase in our HEVC evaluation, and with a larger power reduction here, 66% of power reduction compared with a precise SATD with the two transforms, with the horizontal and vertical transform, the 2D SATD 4x4. This was done with the 4x4 Hadamard matrix. We also have a work with 8x8 Hadamard matrix that is here. But in this work, we did another evaluation, another interesting evaluation. This work was published in LASCAS last year. That we do 3 levels. We have a precise level. We have the 1D, that is 2 columns excluded. So this is the 1D, the same from the another, but for the 8x8. And we have also one column excluded. We are excluding columns of headers of the transforms. And then we evaluated. This is the vertical. We have already approximated only the vertical 8x8 Hadamard transforms. And then we evaluated also compared with precise SATD and also SAD. We compared also the SAD instead of using SATD, compared with precise, and you have here the bit rate results. So you have here also small increases. We have for some videos like this one, 1.32% increase in BD rate for the same quality, or in this video 1.52. But in most videos have 0.8 or 0.7, 0.6. And this is also larger for this when we are excluding 3 columns. Actually, 4 columns is the 1D, but 3 columns is these are all the approximations are better than excluding the whole vertical transform. I'm correcting the previous information. And we have different levels of approximation. And we have SAD only to compare if the approximations here are lower than, are impacting more than SAD. So if they are impacting more, then we can use SAD instead of SATD, because SAD is the allow complexity metric. But 3 columns was our limit in this work, in the HEVC evaluations, of course. And we can see here an interesting power reduction also compared with the precise SATD. Okay, some more details you can see in the papers also. So another case study here is SAD. There are actually a lot of papers using approximate arithmetic operators inside the SAD. So this is we found a lot of works. For example, using approximate adders in the different parts of the SAD hardware accelerator. So we did a different thing here, that we designed an approximate subtractor. We proposed an approximate subtractor. This is actually a work in cooperation with Federal University of Pelotas that is doing by the PhD student. And he proposed this approximate subtractor that approximate the least significant bits of the word of the subtractor by applying imprecision, by doing approximation of these results. And the most significant bits are being done with the full precise subtractor. And we applied in the subtractor of the data path of SAD hardware architecture, the hardware accelerator. They have the subtractor, the absolute calculator, and another 3 here. So we did only this replacement, and we also before that we compared these subtractors with another approximate subtractors that we found in the literature, like these ones, and also if this lower, that is approximate adder, the lower part of our adder, that is the reference here. And our actually the main goal of our arithmetic operator there is to increase the precision when we apply different levels of imprecision, of bits of imprecision. So our operator is more precise than the related work, approximate subtractors. And with this, even being more precise, we achieve a power reduction because of this very simple solution here. We achieve a power reduction compared with the tool adder, the precise adder that is derived in the synthesis tool. So we can design the messages that we can design this data path with our adder instead of using the minus sign in the hardware description level description. So, and then we can have a power reduction, and also you can have a power reduction compared with the lower approximate adder. Okay. We are now evaluating. This is a very preliminary work, but we are now the student is now evaluating the BD rate impacting with this strategy in the VVC encoder. So we are actually now working with VVC in this particular work here. Okay, so let's see some conclusions of this talk. So the message is that hardware accelerators are key to develop a real-time power and energy efficient video codecs. So it's not possible now to have real time and now actually real time with good quality video in a power and energy efficient way when we have a video codec system. And I'm working in this direction now that approximate computing is bringing additional power energy reduction on hardware accelerators. So we are not only using hardware accelerator and low power techniques in hardware accelerators, but also bringing the approximate computing techniques in these hardware accelerators to achieve additional power and energy reduction. Okay, we mostly, as you see, we mostly used actually application hardware techniques, not only putting the approximate arithmetic operator in the hardware accelerator that we have. We are looking for some things that we can do in application that derives a more energy and power efficient hardware accelerator that does not increase a lot the bit rate for the same video quality. So we are using mostly the BD rate metric, and we saw in this works in our experience that this metric could be used to evaluate the compression efficient drop of video encoders when using approximation. Okay, we are working now on new standards like the VVC. We don't have a published work yet with VVC and approximate computing. We are working on it. And also with AV1, that another codec, an open source codec developed by Alliance for Open Media in 2018 that I did not mention here. Maybe some colleague can give a talk targeting AV1, maybe. We are working also with this cross-layer approximation, like applying approximation different abstraction levels, like in the application, circuit, hardware architecture, hardware accelerator. And the important to us is that this approximation is tuned to the video coding application. It's an intelligent approximation that is not removing the coding efficiencies of the new standards bring. And we also working on accurate configurable hardware architectures. We have now a paper that's going to appear in SBCCI 2021 this year. There's an accuracy configurable ICTD hardware architecture for one of these accelerators that I discussed today. And there are a lot of more challenges to target. If you are interested, and I'm interested also with approximate storage. I never worked with this, but I'm interested in starting looking with this problem, that is the memory problem. In video, it is a very interesting problem, because memory consumes a lot of power, and it consumes a lot of space in the chip. And also automatic synthesis of approximate hardware accelerators that we can do, because we are doing by hand this approximate hardware accelerators, like describing them with hardware description languages and doing the normal synthesis flow, the ASIC flow, and also applying machine learning in all these phases, like for automatic synthesis, or for deciding which approximation is more in each scenario in a Core's configurable hardware architecture. So there are a lot more challenges open here in this field. So I'd like to thank again the audience, Professor Hayes that have done the invitation. This is a very interesting series of talks, and also Mateus for chairing this session. I'm open for questions. Thank you, Mateus. Thank you, everybody.
Thank you very much, Claudio. It was a very enlightening lecture. We can see that you have a very broad experience in this field. You have lots of references. Well, I already knew that, but it's good that you can show everyone how much you've accomplished in this particular field. So congratulations once again.
Okay, thank you.
I would like to take questions from the audience. So if anyone has questions right now, feel free to type your questions in the chat that you have access to. I think I have at least a comment from Professor Altamiro Suzin. He said he congratulated you for your talk. Congratulations. And he says, about multi-core, I'd like to propose a discussion. On the taxonomy point of view, I think that we may call them as a multi-core. I think that actually there's a follow-up.
Yes,
there's a follow-up.
Below.
And then he goes like NP core if they are processors homogeneously in processors. And if they are not homogeneous, then heterogeneous. That's a difficult part. And then accelerator as a special core, which is like when you have a more specific core, then you can call it accelerator. And then he proposes another term, which is hierarchical if there are some cluster of connection. This may continue on the communication channels, bus, segmented buses, hierarchical buses, network on chips, and so on and so forth. Would you like to comment on this comment?
Yes. Okay, thank you, Suzin. Suzin was actually my advisor in the master studies. So hello, Suzin. It's nice that you are attending the talk. And actually, Suzin also he always have this philosophical thoughts, and I think we can use this taxonomy, and actually we are going to have heterogeneous. The message here is we are going to have heterogeneous multi-core, like heterogeneous multi-processors, whatever, chips. So we are going to have, in my perspective, some general purpose chips, general purpose cores, and some accelerators attached to these cores that are domain specific, and some are more like dedicated. So and some maybe are going to be reconfigurable also, because we are maybe in some time we are not going to have space for a large number of different accelerators, a dedicated accelerator. So maybe they are going to be domain specific, or maybe they are going to be reconfigurable in such a. So I think industry is moving slowly to this direction, slowly, because we are looking for now some chips. We have already some chips in our cell phones with video coding hardware accelerators. They are mostly patent protected, not patent protected, but secret. So we don't have we don't know what is inside. But maybe we are going to see this, and also I think I agree with you that they are going to be attached with network on chips and this hierarchical network interconnection. So I agree with you, Suzine. Thank you for the interesting question.
Yeah, I think he suggested that we establish a taxonomy for both processing and then the communication infrastructure, right? So
yes,
I completely agree as well. José Rodrigo Zambuja asked, Claudio, can you share opportunities for students right now?
Yes, I'm open for student applications. Actually, I moved recently for this Federal University of Rio Grande do Sul, and now I'm looking. I'm in the process of making my group now in this new university. So I'm always open for student applications in these fields. Like if you like video coding and hardware design, you are going to like working with these new standards and so on. So we are going to tell after the talk that the microelectronics graduate program is with master applications open. So maybe I'm going to talk more about this. Thanks, Jose, for the.
Yeah, just reaffirming what Claudio said, we have a very strong research in video coding here in our region, and Claudio is definitely one of the most important one of the most important researchers in this field. So
yeah, more or less,
he is definitely someone to look up to, and to look for opportunities. Okay.
Yeah.
We then have a question from Fabio. Thanks for the nice talk, Claudio. Besides video coding, can you tell any other applications suitable for approximate hardware design?
Yes, thank you, Fabio. It was also my colleague
Hello,
in
Fabio.
the master studies and also at CETEC. Fabio, yes, approximate computing is applied in hardware accelerators for neural networks, for image processing, and maybe audio processing also. A lot of applications are maybe computer vision. I don't have. I don't remember any work, but maybe computer vision also. We are seeing a lot of approximate computing techniques being applied in all these applications. That mostly the applications that can tolerate some errors, right? We are not going to apply approximate computing in medical device because we don't have to have errors for example, in medical images. I'm not going to work. Maybe some people convince me, but I'm not going to. I think it's not possible to work with medical devices with approximate computing. Maybe it's possible, but and also some control software for robotics or automate cars and so on. But there are many applications that can tolerate errors, like this consumer electronics, video, image, and so on, computer vision. So I think these are some examples.
Yeah, definitely. There are a lot of filters, right, applied in computer vision, and many of these filters, they are not the optimal filters in most cases. So approximating them is also a possibility. Makes sense.
Yes.
I'm not sure if we have any more questions. Feel free to ask, guys. While we wait for questions from the audience, I have some questions as well. Claudio, you talked a lot about approximation and your contributions in this field for video coding, but it's also looking at the encoder side, right? Can you tell us about how can these approximate techniques be applied for decoders as well? Because they are broadly employed as well, so maybe approximation could be helpful here, or it doesn't really apply. What do you think? What is your opinion?
Yes, it's more difficult. There's an interesting question because it's more difficult to apply because in some manner we are changing the decoder that is standardized, right? So as the decoder process is wholly standardized, if we are approximating for example, some transform, some prediction, we are maybe changing the standard, and maybe it's not going to be compatible because, for example, if you generate a different reference frame for another prediction, maybe it's going to be different and generate a displacement with the encoder, and it's not going to work. But don't know, maybe in the post-processing of image after decoding, we can do some approximation. I don't know, or if you see in the hardware some opportunity to do it without errors, but it's not so much approximate computing. So I don't see any. I see a more difficult. I see it's more difficult to apply to video decoders. Actually, VVC has some now some how do you say, some they have actually SAD. They have some I forgot the word, but they changed the motion vectors a little bit at the decoder side, but I don't have I'm not aware of this actually. I don't see if we can do approximation there and not having a crash in the system. Actually, this is our philosophy, that we are applying this in the encoder side because you don't have incompatible bit stream. This was our principle at the beginning. We don't have to have an error in the image and also and an error in the bit stream that the decoder is not able to decode it. This is an approach that if you can afford it, okay, then maybe some frames you are going to lose, and then we are getting, if you see a random access configuration, we can wait for the next intra prediction and then do the decoding again. But this was not our philosophy. Our philosophy was to not introducing errors in the bit stream because this is standardized. So we are introducing errors in some optimization, random rate distortion optimization point, that we can do some approximation that the message is that we are predicting a block approximately, and then maybe this prediction is not going to be chosen, or this is going to be chosen, but the motion compensation is precise, and then we are not changing the bit stream, and also in at the decoder side we are not changing anything. So because in the encoder is more complex, so this is also a point. The encoder is very complex. The decoder we can achieve real time with not so much computer complexity. So I think I don't see if I answered your question, but it's a very interesting question.
It's not, yeah, it's open for discussion, I think, right?
Yes,
because I think I agree with you. I think you can, implement approximate techniques in the decoder, but this will require changing the norm, right? Changing the standard itself, because otherwise the drift error will make it infeasible. But it's not impossible. AV1 is doing something like that, in my opinion. So, as far as I know, so I think that it is possible. It's just more work, right?
As soon as this is introduced in the standard, we can do it. We can introduce these techniques in the standard, in the next standards.
Yes, exactly.
Actually, AV1 has some smaller filters for low complexity scenarios that they use, and they can change the filters at the encoder, and then the decoder is able to reconstruct it. So if we include these techniques in the standard, that is a very interesting, because we don't have this drift, and we don't propagate these errors to another frames of the video.
Exactly. Yes. We have another question from Fabio. Is approximate computing suitable for every video encoding step? I imagine that the answer is no, but what are the criteria to drive this choice?
Yes, this is a very interesting question that is very related to your question, because I think no. Actually, Fabio has an important work with entropy coding, and I think it's not, maybe it's not, I don't see a possibility to apply approximate computing in entropy encoding, because this is a lossless process. So maybe if has some decision, then you can do it, but it's the same that we are discussing here. If you do an approximation that applies an error to the bit stream, the decoder will not going to be able to decode it in the current standards. But if we consider this possibility in a next video coding standard, then maybe we can consider this approximation possibility at the decoder at the standard, and then we can do that. Maybe that's a possibility.
Okay, very good. I have another question. I'm not sure how much time we have left.
Yeah, I don't know if we have.
Sorry to bore you for such a long time. It's just that
the patience is the time. The patience of the audience.
But anyway, I see that you have works in application level approximation, let's say, where you change the way you compute the SATD and stuff like that. And you also have logical block approximations, right? Because you actually go there inside the operating units and change the subtraction or the adder, right? So did you ever compare your solutions in a cross-layer way, like where you apply the application level approximation and combined with the logical block approximation, and see how these guys work together? Did you ever do something like that?
Yeah, we are trying to do now this with this PhD student at the Federal University of Pelotas. We are trying to combine some approximations in different application, in different levels, like application and operators, and see what's going on. So we have never done that, but I see it's an interesting opportunity, because we see different gains in each level. We saw that it is very difficult to achieve a large power reduction changing the operators, because and there are a lot of works doing this, and this is very clear now for the community, and maybe if you combine different layers, that we are going to have more larger power reduction and energy reduction results. But we are doing it now and we don't have the results yet. So let's maybe another talk.
Okay, yeah.
In another conference or
Stay
something.
tuned. Okay, that's good to know. All right, I'm curious to see the results. Okay, do we have any more questions from the audience? Feel free to make a question, guys. I think that everyone is already satisfied.
Okay, thanks again, everyone.
Yeah, if there are no more questions, thank you very much, Claudio, for your very enlightening talk once again. It was very interesting. The discussion afterwards also was very good, so thank you.
Okay, thank you. And I'm actually working with Mateus in some approximate computing stuff together. So thank you. Also, I also want to thank my former students and the research collaborators like Mateus and Leonardo and Bruno, Luciano also, and many people that collaborate in these works. Sergio Bumpy also. This is done with collaboration of many people. So let's maybe I don't see Ricardo Reis here. I don't see if he's already gone. So I'm going to use this time to announce the next events. It can be Mateus?
Yes, of course.
Okay,
I
let's
think
do that.
Jose is helping us here on the technical side.
Okay. I'm going to share my screen again. Okay, I don't know if you see my screen.
Yes, I can see your screen.
Okay, this is my talk. So in the next week we are going to have this very interesting talk by Alan Wong from Ensilica, UK. He's going to talk about enabling the next generation always connected cars. And there is also an important announcement that Ensilica is going to open a team in Brazil. So Júlio Leão is going to announce this in this talk. It's July 22 next week. And also in the next day, we have the CASS talk from Dr. Vladimir Alves. He's the CTO of NGD Systems in USA. He's going to talk about computational storage and its applications for machine learning. And also we have, as I said, we have open
that's
positions.
The third slide, right?
Sorry?
The slides are not moving.
The slides are not moving, okay.
Yeah.
What's going on?
I don't know. Now it's the third slide. Yeah, with Dr. Vladimir.
Okay, so and now?
It's still the third one. I think that your full screen projection is not being projected. You have to use use the PowerPoint because it's very clear to me. So you can use the PowerPoint.
Okay, I can use this. So then this talk in July 23 is from Vladimir Alves, the CTO of NHD Systems in USA. Okay, he's going to talk about computational storage and its application for machine learning. And here we have the announcement of open positions of the PG Micro, that is the graduate program, the only graduate program dedicated to microelectronics in Brazil. So the master open positions is open until 23 July, with the students are going to start in August. And the doctor positions are open in a continuous flow. So in every month, there's a selection process for doctor students, PhD students. So so we have PG Micro many research lines, and also we have this more hardware design line that I'm part of. So I think it's okay. So thank you again. I don't know if you want to say the last message.
No, just stay tuned for the next talks, everyone. Thank you once again for the invitation. Thank you very much, Claudio, once again for your talk. And we'll see you next time.
Okay, see you next week. Bye-bye.